We're going to talk about measures of center and variation now for our histograms. You can see some of the shapes that we drew in our last lesson. Skewed left, where the tail is pulled off to the left. Skewed right here, where the tail is pulled off to the right. And this one we called symmetric, but we're looking at a very specific symmetric shape called normal. We'll come back to this in a minute. Now, I haven't drawn the bars for the bar graph. You saw in the last section sometimes they outline the shapes of those bars with this curve. We need to know and understand that there are bars under here, and this just shows us the rough shape of those. So, for skewed left and skewed right, the measure of center that we're going to use is the median. And the variation that we use is the 5-number summary. That's the 5 points we use to build our box and whisker plot. They were the minimum, the first quartile, the median, and we see that show up here and here, the third quartile, and the maximum. These numbers will give you a good idea of where the shape is found, where the data lies, and how it's broken down, how it varies from one end to the other. When we use a normal distribution right here, we're going to change things a little bit. This uses the mean, because the mean finds itself right in the center, and it works really well with the measure of variation of standard deviation. So with a normal curve, we're going to use mean as our center, standard deviation as our variation, and we'll see how those are related in just a second. I want to talk about the name. The name normal is chosen because this is often found in normal everyday situations. We'll see a couple of examples in just a minute. The alternate name for this is bell curve because this kind of looks like the shape of a bell. These are interchangeable. It doesn't matter which one you use. Let's take a look now about what makes our normal distribution so powerful. You can see that I've got the outline shape of the bell curve right here, and I've got it broken down into different sections in the following way. This X bar right here is the mean, which is our average for this right here in the center. This little symbol right here, it looks kind of like a squished down 6, is actually a sigma. It's a Greek letter that stands for the standard deviation. So, when we have 1 sigma, that simply means it is 1 standard deviation away from our mean. So if we know the mean, the number for it, and we know the standard deviation, we can put the value for our mean here and then add a standard deviation to get to this spot, add 2 standard deviations to get to that section, add 3 standard deviations to get to this section. The other side is symmetric, so this -1 sigma simply means we're going to go 1 standard deviation to the left, 2 standard deviations, 3 standard deviations, and so forth. We will either be given the standard deviation or we can gather data and calculate that the way we saw in our last videos. Now, these percentages are the same for every single normal curve. These will change, but this will always stay the same, and that's where we get the strength of it. So you can see this 34.1% right here and here tells us that between our mean and where we get to when we go 1 standard deviation away, 34.1% of our data is in that area. Same with over here, 34.1%. As we get farther out, there's less and less data, 13.6 and 2.1%. So if you can memorize one side, you've got both sides memorized. I love the symmetry on that. We also use that symmetry to get these percentages down here. If we take and put these two areas together, all the way from 1 standard deviation below to 1 standard deviation above, that gives us 68.2%, or in other words, just these two added together. As we continue outward, we get an extra 13.6%, and then 2.1% to give us the 95.4 when we go out 2 standard deviations, and the 99.7 when we go out 3 standard deviations. So let's take a look at a couple of real-life situations. This is data that I've found online, so I hope it's accurate. It's about the SAT and the heights of adult women in America. These both end up being normal distributions. If you were to make a histogram of those, they would have that normal shape or the bell shape. So I'm going to go ahead and draw that down. And we're going to break this down into the categories using our mean and standard deviation. So the mean is 1,059, and this comes from data reported by the SAT test itself. So right in the center here, we have our average score is 1059. Now, we often want to know approximately how people compare to the rest of the population, and so most people aren't going to be right here exactly on the average. They will be somewhere close to the average. So we're going to break this down by going through our standard deviations to the side. So I'm going to go one standard deviation this way, which is 210. So from the mean, I'm going to increase by 210. That gives us now a measure of 1,269. Now, from our last picture, you need to make sure you have that memorized. We know that between these two values, because it's normally distributed, that is 34.1% of the population. So 34.1% of people who take the SAT test will be somewhere between 1,059 and 1,269. We can go the other way as well by subtracting our standard deviation, which is 210. If I subtract 210 from that, I get 849. That gives us another 34.1%. And between here and here, put those two categories together, and we get 68.2%. So that is the majority of people. We can say from this statistical analysis that most people will be somewhere between 849 and 1,269. So this is kind of considered the average range for scores. We can continue to break this down by going another standard deviation. So I'm going to again add 210. That puts us at 1,479. And that gives us 13.6% there. And then we're going to go down by another 210. That puts us at 639. And we get another 13.6% there. Put all those together, and we get 95.4%. That is almost everybody. So almost every person that takes the test, except for about 4.5%, are somewhere between 639 and 1,479. We can go out one more standard deviation for this example, and that puts us at 1,689 at this end, and 429 at this end for that extra 2.1%, and that gives us 99.5%. All right, so we've broken this down as far as I want to go for the SAT. We can do the exact same thing for the heights of adult women. Now the picture is going to look almost exactly the same as this. The only thing that we change is the numbers for the data. Our mean is now 64 inches. Well, that's going to go right here in the middle. And our standard deviation is 2.5 inches, so we're going to just add 2.5 to get our numbers to the right and subtract by 2.5s to get our numbers to the left. So here we go. I'm going to leave those percentages there and put our new data. So we get 64. If I add 2.5, that's 66.5. Add another 2.5. That is 69, and add another 2.5, that's 71.5. If I subtract 2.5, that puts me at 61.5, 59, and then 56.5. And then we can add those percentages, 68.2%. And then the 95.4% and the 99.5%. I should have just left these earlier. So 68% of the adult female population in the United States is somewhere between 61.5 inches and 66.5 inches, and we can kind of start to break that down into categories and analyze if people are around average or if they're taller than average or shorter than average. And that gives us some powerful tools that we can use in the world of statistics. So remember these percentages. Thank you very much.